Hello friends, very good afternoon. Myself Dr. M.H. Annaya. In today's video on Machine Design 1, we are going to learn how to design a screw jaw for a given capacity. Friends, let's see what is the question we have for today's video. The question reads like this. Design the following parts of a screw jaw to lift load of 10 kilonewton is the load to be raised, assuming suitable materials and factor of safety. So this is a very basic problem. That is the problem with minimum data given. You should be able to find out or design the components of the screw jack. Namely, you have been asked to design a screw jack, a nut, and the handle or the lever. Friends, you know a screw jack is used to lift load, to raise a load or to lower a load. And here what happens, basically we have got four components in this. That is the screw rod, which is made of steel and it will have square threads. And we have got the second component, the nut. It may be made of cast iron or bronze. Third, you got a Tommy lever or a handle or a lever which is used to operate the screw jack. That is to raise the load and to lower the load. And friends, we have been asked to design all these components. And let us start the design from one by the component, say the design of the screw jack. That is A, to design the screw to say screw rod. Friends, I told you this screw rod is of square cross section. That is, square threads are used, and on this screw rod, when the load is being raised or lowered, this is subjected to a compressive load, and hence the type of stress induced in this screw rod is a compressive stress. So we can start the design of this screw rod with this concept. The screw rod is subjected to compression and hence the compressive stress sigma c in the rod is load over area. So this is compressive stress. W is the load that is to be lifted and A is area of cross section, that we call it as AC, the core area, that is the minimum area of cross section of the square thread. So friends, here we can rewrite this as AC equal to W by sigma C. So this is the minimum core area of the screw rod required to raise that load or to lower the load. Friends, here this W is the total load to be raised, that is 10 kilonewton. So we will convert that to Newton, that is 10 into 10 to the power of 3 Newton is the load to be raised. And friends, this sigma C is the compressive stress, permissible compressive stress in the rod. So in most of the cases, the value will be specified or the material will be specified. And here, they are not given either the value of sigma c or the material used for the screw rod. So we should be able to select some material. Generally, 40C8, C45 steel rod is used, carbon steel. So we have to obtain what is called sigma c, that is the value of the compressive stress for C45 steel. If you refer to the machine design data handbook, the value of sigma U ultimate stress is given to be 618 Newton per mm square. This is the ultimate value. But we want a design value of the compressive stress. So the design values, the ultimate value by factor of safety. Ultimate could be the yield value. Okay, so here sigma u is so much. So I make use of a factor of safety, not given in the question, that will be usually given. Factor of safety is equal to say. So the permissible value sigma c can be taken equal to sigma u by factor of safety. Sigma u is 618. You can refer to this data handbook and this value is available. Divided by 3. So friend, this works out to 206 Newton per mm square. This is the value of the permissible compressive stress. So based on this value, we will get what is called the core area of this. So I will just move back to this and again write down here the values. That is sigma c is 203, that is equal to W is 10 into 10 to the power of 3 divided by core area. So friends, if you simplify this, you get the core area of the square rod, that is normal square rod used in the problem, works out to 48.54 millimeter square. This is the area, that is the minimum area of the rod required to sustain this load of 10 kilonewton. So higher the load, more will be the core area required. That is very obvious and all of you know. Friends, after obtaining this value of sigma c, that's our AC, the core area, you will have to refer to the square thread of normal series, and corresponding to this value, you will have a definite value of screw rod required, that is outside dia, which is called nominal dia, core dia, and the pitch. Friends, remember, it will have, the square thread will have a profile like this, but all of you should know. So it will have like this. So I will tell you what the relation existing between these various parameters. So friends, the outermost diameter is called the nominal diameter D. The inside diameter is called the core dia, that is small d1. Depth of cut is equal to pitch by 2. Again, this depth of cut is pitch by 2. And friends, if you refer to this, you can say the outside dia D is equal to d1 plus pitch by 2 plus pitch by 2. So d1 plus p. This is the relation that exists between the nominal dia or the outside diameter of the thread, the core dia d1, and the pitch. Pitch is this value. So friends, now we have this core area, and when you refer to the table on this square threaded rod, so you will have a minimum value of 227. So this value is not available. If you refer to the handbook, minimum value will be 227 mm square is the core area that is available in the table. So using this value of core area, we should be able to obtain, I will say here, corresponding to area, that is AC equal to 227 mm square, we have, that is referring to normal series square thread, comma, we have, I'll just write down what are the values of this. So we have the core area 227, and the value of this outside diameter is D is equal to 22 mm. Then D1 is the core dia, minimum dia is 17 mm, and pitch is equal to 5 mm. Friends, these are the dimensions of screw rod. I will say here, dimensions of screw rod. You should just show them like this. That is, D is the nominal dia or outside dia is 22. Core dia or the minimum dia is 17 mm, and pitch of the threads is equal to 5 mm. Remember, this value D is B1 plus P. So 17 plus 5 is equal to 22 mm. Friends, this is how we find out the value of the various dimensions of this screw rod, namely the outside dia, the core dia, and the pitch. Friends, next let us move on to the design of nut. Friends, the screw rod is threaded externally, and corresponding to this there will be a matching nut in which the screw rod moves. So friends, let us see how to find out or how to design a nut. Friends, generally, these nuts are made of either cast iron or bronze. So, depending on the material, there will be what is called a bearing pressure or a bearing stress. So, in the design of this nut, we need to find out what should be the number of threads cut inside the nut, and also what is the height of the nut or length of the nut. Friends, if you refer to the machine design data handbook, it is given that I is number of threads is given by the formula 4W divided by sigma b dash by d square minus d1 square, sigma dash into pi divided by sigma b dash by d square minus d1 square. Friends, W is the load, we know the value. D is the major dia, D1 is the minor dia, and we have to find out what is the value of this sigma b dash. Friends, sigma dash b dash will not be given. That is the bearing pressure or bearing stress. I told you in the beginning of this, the nut is made of either cast iron or bronze. So for both of these material, the average value of sigma b dash obtained from machine design data handbook is approximately 15 MPa. So here I'll write down W is 10 into 10 to the power of 3 Newton. The load is given. Sigma by dash is equal to 15 Newton per mm square obtained from machine design handbook MDH. D value D is 22, D1 is 17 mm. So friends, if you substitute all these values, you will get the minimum number of threads required. I is the minimum number of threads cut in the nut, works out to a value 4.25. So this is the minimum number of threads. I is equal to 4.25. Friends, generally we round it off to 5 threads. So there should be 5 threads cut inside the nut, whether it is made of cast iron or bronze. So next comes what is called finding out what should be the length of the nut. So we have a formula again similar to this, that the length of nut is ln, L suffix n, is equal to I into pitch. So this is again given in the machine design data handbook. This is given directly. So we have got this I is equal to 5 threads, pitch is equal to 5 millimeter. So you get totally 25 millimeter as the length of nut. So 5 into 5. So this is the length of nut. So design of nut is over, wherein you have found out the number of threads required and what is the length of the nut, or is also called the height of the nut. Friends, after this, we will move to this design of handle. Friends, the handle is generally made of circular cross section because that becomes easy for holding and applying the load. So it will have a diameter DH and length is equal to LH. So friends, I will just simply write a sketch like this and show that there is a rod which has got a diameter DH and the length of this is LH. So the product of these two, that is, you have to find out what is LH, length of the handle, and this is DH, is the diameter of the handle. That is what we find out in this. Friends, to find out this LH, we can start or go ahead with a simple formula that the length of handle is equal to the torque divided by, torque means torque required to raise the load, divided by F. So this is a very simple relation. Torque will have the unit Newton millimeter, length is equal to have a unit millimeter. F is the human effort, that is the effort or the pull an average man can apply. That will be generally 300 Newton. So what I do, I will just rewrite this as MT divided by 300. So if you are able to find out what is the value of MT, that is the torque required to raise the load, we can divide one by the other and obtain the length of the handle LH. So for this, first of all, we will have to calculate what is this MT. And friends, if you refer to machine design data handbook, the equation for the torque MT is given by this relation W d2 by 2 tan alpha plus mu divided by 1 minus mu tan alpha plus mu c dc by 2. This is the equation available in the machine design data handbook to calculate MT, the torque required to raise the load or to lift the load. Friends, if you want to find out what is the torque required to lower the load, so the only difference is in place of plus mu, you will have minus mu. That's all the difference. This equation is available again in the machine design handbook. Friends, let's see what these parameters are one by one. Friends, here this W is the load, load that is 10 into 10 to the power of 3 Newton. That is given in the question itself. This D2 stands for mean dia of thread. Mean dia of thread or the screw rod. That is given by outside dia plus inside dia divided by 2. Outside dia is, we have calculated 27 and plus this D is 17. Sorry, this is 27. Yeah, 22 and 17, not 27. This is 22 and this is 17. Yeah, divided by 2. So this will be 22 plus say 18, 40 by 2 or 39 by 2 is that is 39 by 2 is 19.5. 19.5 is the mean diameter of the thread. Outside dia plus inside dia by 2. So we have got the value. Then friends, this tan alpha is equal to L over pi d2 is again given in MDH, machine design data handbook, where this term L stands for the lead. So the value of this L is equal to lead. What is the meaning of the lead? Friends, if you have a screw rod and a nut, holding one of them stationary, if you give one complete rotation to the other member, suppose holding this screw rod stationary, if you give one complete rotation to the nut, the distance through which this nut advances on the screw rod is called the lead. So this lead is equal to pitch for single stud thread and it is equal to 2 pitch for double stud thread. Final, or in other words, it is 3 times pitch for triple stud thread and so on. So friends, I will assume this to be a single stud thread and the value of this is going to be 5 millimeter. We have taken already from the table. And then tan alpha you will be able to calculate. Friends, mu is the coefficient of thread friction. Again, if not given, it is available in the table. And for the combination of the screw rod that is steel and the nut is cast iron, the value of mu is 0.147 from table. That is corresponding to screw rod of steel and the nut of cast iron is a value available in MDH. Then that friends mu c is the coefficient of collar friction. Again from the table it is 0.14 for the same combination of these two. And then friends you are left with this DC. Friends, DC is the collar diameter. So collar is a part of that nut which rests on the base of the screw, base of the what's called jack. So here this DC is approximated as 1.5 times D. Is only an assumption if nothing is given. So we can take it as 1.5 times small d, where d is the diameter of the screw rod. And friends, with all this substitution, if you simplify this, you get a value of this mt as 46112.7. 46112.7. It's a torque, Newton millimeter. So once you have this torque, then the length of the handle is this torque divided by the effort, that is 46112.7 divided by say 300 we have taken. And friends, this works out to LH value as 153.71. 153.71 millimeter. So we have got the length of the handle. So finally, we have to find out what should be the diameter of the handle, because these are the only two parameters you have to find out for a screw rod. So friends, to find DH, DH means dia of handle or diameter of the lever used to lift the load. Friends, you know this, while raising the load, the tommy bar or the rod used to operate the job is subjected to bending, and hence the bending stress in the rod, we can write down bending stress in handle is given by the basic formula is sigma b. Bending stress is mv by zb, a basic equation, mv by zb. So what is mv, friends? Friends, mv is equal to f into, see, bending moment. You have this length L, the effort applied at the end into length will give you the bending moment, f into LH plus some 200 mm. You can ask me what is that 200. Friends, while operating this screw jaws, we don't operate using a single hand like this. Maybe you will have to have a hand to hold like this. So approximately I will take that additional length of the rod as LH plus 200. This 200 is to accommodate the hand to operate this screw jaw. So friends, you know the value of this F300, LH you have calculated, this 200 we have assumed, and this works out to some value. We will be able to find out. Then what is ZB? Friends, while designing any of the component, one should be thorough with the fundamentals of strength of material. Here friends, this ZB is equal to section modulus. Section modulus. That is given by the formula I by C. I for a circular cross section is pi t to the power of 4 by 64. C is equal to diameter by 2. And this works out to pi d cube by 32. And here this d is our dh. So friends, here if you substitute in this formula, let's see what happens. So this bending stress, generally for the steels, the tensile stress and compressive stress will be almost same. So I will take this as a value equal to, that is 618 by 3, that is 206 is the value of bending stress. That is MB value. We know this as F into LH plus 200 divided by ZB is pi d cube by 32 or pi dh cube by 32. I will take to numerator. I know this value. This we have calculated, and you will be able to arrive at the value of dh. That is the diameter of the handle required for this is works out to dh as 19 millimeter. Friends, this is how we calculate the three components, mainly the screw rod, then you have the nut, and again the design of the lever. These are the three important parameters, and apart from this, there will be the relation for the dimensions of the body, which is conical in shape, frustum of a cone like thing. So friends, I am very sure that all of you would have followed the procedure adopted to design a screw jack. The main components, namely the handle, the screw rod, and handle screw rod and the nut. So I will just revise again. The screw rod is designed based on the concept that it is subjected to compression due to load. Based on the compressive stress, we find out the minimum core area required, and referring to table in the machine design data handbook for square threads of normal series, we obtain the outside diameter of the thread, namely D, inside diameter, that's called cold dia, small d1, and the pitch. And remember, in this screw rod, the outside diameter is equal to inside dia plus pitch. Next friends, moving on to the second component, nut. Nut is made of either cast iron or bronze, and we find out the length of the nut by finding out the number of threads and multiplying that by pitch. The number of threads we have calculated based on the load and the bearing pressure. We have got the value. And finally, friends, the rod that is designed, rod is also called Tommy bar or the lever used to operate the jack. So friends, there we are going to design the component by finding out what is the bending moment this is to withstand. So it will have a circular cross section which becomes easy for holding and applying the effort, and that is designed based on some assumption of the effort that a human can apply, a healthy person like 300 to 400 Newton. So friends, please go through the complete video, and if you like this video, do share it with all your friends without fail. Thank you for watching my YouTube video. Have a blessed day.